Right, we're starting the recording. I do apologize yesterday. My computer did go through some mandatory updates, which I had no control of, and those updates took about 45 minutes to do. So, that's what happened yesterday. So unfortunately, the PowerPoint slides that I was working on were not saved. The computer just shut off. It didn't give me an option to save them. So, you'll have to rely on the video if you want help on the homework questions for 1 through 20. I'm going to go ahead and share my screen, and we're going to finish the chapter 5 homework up today. We'll start at question 21, so you can go ahead and open up your homework and go to 21. I'm just going to plug in my pad. Move it here. So we'll start at 21. There we go. So it says select the choice that best describes the relationship of the pair of compounds. So they give us two compounds on 21, and we have to select the relationship, and the relationship is they are enantiomers. The reason being is if you turn the compound on the right 180 degrees, the hydrogens are going to line up with the hydrogens, and the chlorine will line up with the chlorine. So that's why they're enantiomers. They'll be mirror images. And we'll do 22 on the same slide. For this compound, it gives us two compounds. We have to determine, if they're identical, enantiomers, diastereomers, constitutional isomers. So let me take a look at this for a second. And they are identical. What you have to do with this one is they show compound 1 and compound 2. So leave compound 1 alone. And what you're going to do for compound 2, you're going to flip it like this. Now, if you flip it like that, then that methyl group will go up, the chlorine will go up, and the hydrogen and chlorine will fall in place. So they are identical. So you just have to make that transition how I showed on the screen. It's 22. Any questions on 21 or 22? All right, we'll go to 23 then. 23 says the asymmetric carbons on compound A are located. So let me see. It's not showing me. So the asymmetric carbons on compound A, they're going to be on carbons 2 and 3. So you're going to select that for A. It says, given the Lewis structure of compound A, is there a plane of symmetry? You're going to put cannot be determined. For structure B, it says the asymmetric compound on carbon B are located on, it's going to be on the carbon with the methyl substituent. On the methyl substituent, there's an oxygen there. Here is going to be where it's going to be at. So it's going to be on the carbon with the methyl substituent. And given the structure of compound B, is there a plane of symmetry? And no, there's no plane of symmetry. For compound C, it says the asymmetric carbon on compound C is located on, and that's going to be none for C. Because if you look at the substituent, the only possible place it could be, it'd be right here. There's a hydrogen here, you know, and there's a methyl group. But if you go down this line right here and here, it's the same thing. It's identical. So that's why it's going to be none. So given this, is there a plane of symmetry? And yes, there would be a plane of symmetry. And if we can imagine the plane of symmetry, if I draw that methyl group and that hydrogen overlapping, it'd be right down the middle like that. So that's where the plane of symmetry would be. So that's 23. '22 has name. Let's see. Okay, so we did miss a part on 22. Let's go back to 22. So let me see. So there's a naming part on 22. Says the correct IUPAC names are, let me see. They're both going to be in the R direction for both of them. And it's pentane is the longest group. And since they're identical, they're going to have the same name, right? So you have to pick the one that has 2R, 3R, 2,3 dichloro pentane. And like I said, since they're identical, you're going to pick the same one for the second one too. All right, so that's 22. 23 is here. And let's go to 24. 24 says, give the proper IUPAC name for the molecule shown as a Fisher projection. Remember, for Fisher projections, we have this, and then this, if it's on a horizontal plane, it's going to be coming out. If it's on a vertical plane, it's going to be going in. So we have Cl, CH3, so first we have to decide how long is the longest chain. We have, let me see, 1, 2, so you have 1, 2, 3, 4. So you know that's going to be butane. So they all have butane. So that's, and the chlorine is going to be in the 2 position. So that gets rid of options 3 and 4. Now we have to determine whether it's R or S. So let me see. R is clockwise, S is counterclockwise. And remember, if the hydrogen's sticking out, you got to reverse it. So we have 1, 2, 3. That'd be going this way. But since this hydrogen's sticking out, we have to flip it. So that means we're going to be in the R position. So it's R2-chloro butane. So 25 is kind of similar. It's R2-chlorobutane, and what they did was they flipped the structure on you. So you're just gonna have to rotate this structure. They put the CH3 group here. But they put the CH3 group here, you're gonna have to flip that hydrogen there. This chlorine is gonna go here, and this CH3 group is gonna go here. That's why it's good to have a model set, to be honest with you, because then you can flip this structure. You know what they did was they they rotated it 90 degrees, and then they did a 100, yeah, then they did a 180-degree rotation this way. But first you do a 90-degree down and 180 degrees horizontal, and that's how you get this configuration. We'll just leave this for 26. The 26 has it shows a molecule. It says, are they chair conformation of the same molecule? And yes, they are. They're identical conformation of the same molecule. So you're gonna pick identical. There's only one option that has identical. (27) it says two disubstituted cyclohexane molecules are depicted. Classify the pair as the same compound, enantiomers, diastereomers, constitutional isomers, or not isomeric. You can see the chlorine is in a different position for this one. So, they're not going to be identical. They're going to be diastereomers. We'll go to a different slide for 28. If it lets me. The 28 shows you two molecules. And what they are is they're going to be enantiomers because they're mirror images of each other. If you flip it this way like this, then what's going to happen is you're going to have the hydrogen here. I mean, if you flip it, let me see, you'll have the, this will be hydrogen, this will be bromine, and then this will be, so you can see that they don't overlap, so they're going to be enantiomers. (29) it says select the true statements. So you're going to select options 1 and 3. Option 1 says a chiral adsorbent is used in chiral chromatography. That is true. And one enantiomer will elute faster than the other. That is also true. So you're going to select options 1 and 3. we go to 30. 30 gives us a bunch of, I'm not going to draw all these structures out, but they give us a bunch of structures, and you have to determine whether they're the E or Z or neither. So option A, that's going to be your, let's see. That's going to be Z. Z is on the same side. Remember, Z is on the same side. So that's where the bigger groups are going to occur. It's the same side. Option B is going to be E. And that's because you have that methyl group right here. So it's going to be E. That's kind of like the trans. C. Let me see. Okay, so the C and D are the same molecule. I get that now. So we have C and D, it's the same molecule. So D is going to be neither. That's going to be the easier one to decide because it's going to be neither because you have that CH2 group. So that'd be identical. Now you have a CH2 group right here. So that's why it's going to be neither. Now let's look at C. C is going to be Z. And the reason for that, you have this big group right here, and then you have that carbon with that oxygen right here. So that's going to be the same side. So that's 30. And but question 31, and this is our last question. We have 4 representations of 2,3-dichlorobutane. It says, which structures are meso? Let me see. So a meso compound contains 2 stereocenters and can be superimposed on its mirror image. So a meso compound contains 2 stereocenters and can be superimposed on its mirror image. So that's the definition. So let's see. So we're going to select B and D. Reason for that is, let me see. This is B right here. D. These are chlorine. This would be S. This would be R. And this would be R and S. Now, if you look at the other ones, option A will have 2 R's, and option D, not D, but C will have 2 S's. What you're going to have to do, you create the mirror image right here, and then you just rotate it. And you can't do that if it has an R, and SS. So you'd create the mirror image, and then when you rotate it, you should get the identical compound. So let me see. So the mirror image would be, so that's your mirror image. And if you rotate this, then it's going to overlap. So that's why B and D work. So that's 31. Any questions? All right, so let's go ahead. I don't see any questions. What I'm going to do is stop sharing. I got to save this. I'm going to save this so I can provide this to you. We'll keep the annotations. This time we'll be able to save them because my computer is not shutting down on me. And I'll be able to load at least, 21 through 31. But unfortunately, the first 20 questions, which I don't like, got deleted because I like to have those PowerPoints myself too. All right, so I'm going to go ahead and open chapter 6 up. So it looks like our first exam will be covering chapters 1 through 6 because more than likely we'll finish this and then homework either today or tomorrow. I think I only have like around 15 questions on the homework for chapter 6. So your exam will be over chapters 1 through 6. I haven't made the exam yet, so I still need to make the exam, but I will get the exam posted. I'm not sure how many questions are going to be on the exam yet, maybe around 30. Then I'll post the exam, and then you'll have that time frame, what it says in the syllabus to do the exam. And then please do the exam. There will going to be no makeup exams, so please, when the exam comes open, please do it. So I'll give you about a minute to open up the homework, or not the homework, the PowerPoints, and we'll continue on. Okay, let's go ahead and start on chapter 6. This chapter has to do with chemical reactivity. You're going to see enthalpy. We'll look at entropy. They have some delta G. Hold on for just a second. I have my dogs barking. I apologize. All right, I think they settled down. This chapter will also introduce you to some arrow pushing. And what do I mean by arrow pushing? Let me get my pen out. Let's just say we have some type of electrophilic site, and we have a nucleophile, and it's going to come in like this, push the arrows. That's what we mean by arrow pushing. So enthalpy is the heat energy exchange between the reaction and its surroundings. And this goes into breaking bonds. So you'll see that there's tables of enthalpy charts for bond breaking. You don't have to memorize the numbers, just use the chart, as you need it. Here, we talked about energy diagrams. Here you have n atomic orbitals. Here's 1. Here's 2, and that gives you n molecular orbitals. So n AOs equals n MOs, and then you see you have 2 molecular orbitals right here. So bonds can break either homolytically or heterolytically. So this is a homolytic cleavage where each the X and the Y each get 1 electron. A heterolytic cleavage, the Y in this case gets 2 electrons. So bond dissociation energy, or delta H for bond breaking, corresponds to homolytic bond cleavage. And here's the tables that I was mentioning before regarding bond dissociation, bond breaking. You don't have to memorize this. This is all a table right here provided for you. And there's a lot more bond breaking than this. They just give you an example right here of some common bonds that are broken. Like they said, more bond dissociation energies can be found in table 6.1. So exothermic reactions are the energy gained by bonds formed. So the energy gained by bonds formed exceeds the energy needed for bonds broken. And usually, you'll have a net sum of a negative. And endothermic energy needed for bonds broken exceeds the stability gained by the bonds formed. So products are less stable than the reactants. So here, if this is our starting materials, and here's our starting materials here, you can see that this went down in energy. So this would be exothermic. Here we're going up. So this would be endothermic. And that's basically what you should be thinking about when you see this. We also give you some tips. Delta H is negative. In this case, delta H is positive. So those are just some helpful tips to help you out. The sign, a positive or negative delta H, indicates that the reaction is exothermic or endothermic. And you saw what the signs would be if they were exo or endo right here. So an energy diagram is often used to describe the kinetics and thermodynamics. Remember, kinetics and thermodynamics are two different things, though. Even though something might be kinetically, or thermodynamically better. So diamond thermodynamically degrades down into graphite. Well, that takes a long time. So kinetically, really, it's not going to happen. So it's two different processes we're looking at. So potential energy is described by the y-axis. The reaction progress is described by the x-axis. Right here, remember the table that, I think they have this in that table, CH, CBr, BR, BR. If they don't, just refer to table 6.1. And that table, what we're referring to, let's just look at one CH and BR, BR. They don't give BR, BR, but they do give CH. I'm not seeing that one either. Fine. Okay, so please refer to table 6.1 to look up these numbers. This bond they're talking about right here, that's this one right here. And this is what they're talking about right here. And the bonds formed, we get one CBr bond right here. And we also form this one right here. So we take our bonds broken minus our bonds formed. So, we have this number here, and it's getting a little messy, so I'm going to do some erasing. Have this, and then likewise on the bonds formed, and we get minus 63. So it's exothermic. If on the exam you need to look up any of the numbers, just please refer to table 6.1. Exothermic and endothermic reactions can occur spontaneously. Most reactions are exothermic, though. It says enthalpy and entropy. Entropy is the amount of disorder. So this is the amount. So, if you have a bunch of blocks, more than likely they're going to fall apart, and then the blocks are going to, drop on the floor, and they're going to be more disordered. So recall that entropy can describe it as a molecular disorder, randomness, or freedom. Entropy is a number of vibrational, rotational, and translational states that the energy of a compound is distributed. So those are some definitions there. And they give a really good example right here. I gave that example of the blocks, but if you have a container and you open this container, it's going to fill up the other container. So more volume equals greater entropy because it's more disordered. When it's closed, and you can think about this, let's just say we had a tank and it's helium, and I release the helium out. Well, then it's going to become more disordered because it mixes everything in the atmosphere. Whereas what's in the tank, now I have it contained, I can fill up balloons with it. So total entropy will determine whether a process is spontaneous. So if delta S is positive, the process is spontaneous. So remember, if delta H was negative, then it was exothermic. But here we're talking about delta S is positive, the process is spontaneous. So delta S is affected most significantly by two factors and will be positive when there are more moles of product than reactant. So here, even though you see A and B, they're combined, right? So it's only 1 mole of, let's just call it a gas. And when we break this gas up into components A and B, now we have component A and component B, which we have 2. You have 1 versus, 1 and 2. So, that's why it's more favorable to go in this direction. When a cyclic compound becomes acyclic, we are making it more entropic. There's more disorder. Here this is more ordered when it's cyclic versus acyclic. So those are 2 examples they give. I'm not concerned with you deriving these equations, to be honest with you. So I don't want to really go into the derivations of these equations, but, I just want to, they're just showing you that they're here. They're trying to show you how to derive Gibbs free energy, but, like I said, here we get to the delta G equation. And if you take this minus T delta S, this is delta G. So that's what they try to do. That's what they did do here. They derived that equation. So, but I'm not concerned that you know how to derive it, just that the equation is right there. So it says consider the following reaction, which is spontaneous. We haven't talked about this, but this would go here, this would go here, and this would go here. And that's how you get this 6-membered ring. Because think about this: you have 1, 2, 3, 4 carbons here. You have 1, 2. So this is how this formation would happen. Since the reaction is spontaneous, delta G must be negative. So delta G equals negative. We also know that T delta S will be negative value because entropy is decreasing. 2 molecules becomes 1. Remember, if entropy is positive, then we're becoming more entropic, right? So if we go in this direction, then we're getting more, entropy is increasing. But that's not the case, so it must be true that delta H is a negative value. So this is going to be a negative value. For delta G to be negative overall. So in other words, the entropy of the surroundings is increasing more than the entropy of the system is increasing. So if a process has a negative delta G, which we saw in the case of, this thing right here, the process is exergonic, and this is an exergonic process right here. It says, notice that the free energy is plotted rather than enthalpy. And that's that. remember to get this, you just had to move this right here, here, and this goes here. So if a process has a positive delta G, the process is non-spontaneous and we're going in the opposite direction. So think about this product right here, and we bust it up into this, and then we bust it up into to that. So if we're gonna break these bonds, then this is gonna be endergonic. And this will favor the reactants. So that means we can break it up into these two products, right? But it's going to take more energy to do that. It's an endergonic process. So it wants to stay over here on the left-hand side. It doesn't want to go to the right-hand side. And that's what that means. This is consider the exergonic process with a negative delta G. An equilibrium will eventually be reached. That means when an equilibrium is reached, we're not forming any more C and D. We're going back in the reverse direction. We're going back in the reverse direction, equally going into the forward direction. So the reverse and the forward directions are equal at equilibrium. So spontaneous process means there will be more products than reactants. So here we see a spontaneous process. The greater the magnitude of delta G, the negative, the greater the equilibrium concentration of products. So if we go down here even further, we'd have more products. If we go up, that means too, let's just say we stop right here, we're not going to have as many products. So you have the three different variations. So this is the middle value. Here's the top end where we're going to have more reactants, and the bottom end, we're going to form more products. And this would be the least amount of products. It says, why doesn't an exergonic process react 100% to give products? Why will some reactants still remain at equilibrium? It says as A and B decrease, collisions between A and B will occur less often. You'll have less A and B to have collisions, so we'll get less opportunity to get C and D. And as I said previously, eventually the forward and reverse reaction rates will be equal. So we're not going to get any more products. An equilibrium constant is used to show the degree to which a reaction is a product or a reactant. Equilibrium constant is just the products over reactants, and the C and D come from this slide right here. See, they have the products, then you have the reactants on the right-hand side. So it's just going to be the C, D over A, B. And they show that to you really nice right here. And delta G equals minus RT natural log of KEQ. So you put this in right here then. So KEQ, delta G, delta S, and delta S, or delta H and delta S are thermodynamic terms. They only describe the relative stability of the products and reactants, but not the rate. So this doesn't describe the rate. So it does not describe rate. And the rate is how fast that reaction is going to proceed. This slide says, note that increasing or decreasing the value of delta G, and what they're talking about is right here. You start with negative 17 going up to positive 17. The value of delta G by about 6 kilojoules per mole corresponds to a 10x change in the equilibrium constant. So they're just talking about this change right here. You see that? If you take 10 to the 3 is 1,000 divided by 100, that's 10, right? That's how you get your 10x change. And you can see, look at the difference with the products at equilibrium. You have 99.9 versus 0.1% if you go all the way down to the bottom. It says, recall that a negative sign for delta G tells us the process is product favored, spontaneous. Positive would be non-spontaneous then. It says this does not tell us anything about the rate or kinetics for the process. So in other words, delta G says nothing about how fast a reaction will occur. It says some spontaneous processes are fast and some spontaneous processes are slow, such as carbon, diamond going into graphite. The reaction rate is a function of the number of molecular collisions that will occur in a given period of time, which is affected by, the following factors. There's affected by the concentration, activation energy. If we're looking at energy diagram, there's an activation energy that'd be right here, and we call this EA. And we can lower the activation energy with catalysts. And this would be using a catalyst. Temperature, if you increase the temperature, usually, you can increase how fast the reaction goes. Geometry and sterics. If it's more if it's something like, let's just have butane versus, something like this, then there's going to be more sterics involved, right? If you have this, 1, 2, 3, 4, 5 versus something like this, even though we have 5 carbons, there's going to be more sterics here. And the presence of a catalyst, and I showed that example right here. So the rate is determined using a rate law. Rate laws always have to be experimentally determined. Rate equals a rate constant times the reactants. So the rate depends on a rate constant and the concentration of the reactants. And like I said, you do have to experimentally do this. And to determine all this stuff right here, this is all experimentally done. So this is experimental. That means you have to go into the lab. I should write better than that. And I mean, since you're not going in the lab, most likely they're going to give you all this information. So we see that this is first order in A, this is second order in A, and this is third order in A. So if this is doubled, the rate is doubled. But when you see that, when you add that square right here, then if you double the rate, if A is doubled, the rate is quadrupled then. But like I said, to determine this, you have to experimentally determine these numbers. Superscripts is what I was looking for. You have to experimentally determine the superscripts. You have to experimentally determine the rates. So they don't go into a whole lot of this rate stuff because that's a separate course called kinetics. I've taken kinetics before, and it's a whole semester course. So they're only giving you a few slides over kinetics. Activation energy is the energy barrier between reactants and products. And we'll do this slide, and then we're going to take a 10-minute break. And activation energy is the minimum amount of energy required for a molecular collision to result in a reaction. And you can lower this activation energy with the catalyst. But that's the definition of activation energy. So let's go ahead and take a break, and we'll be back in 10 minutes. So we'll be back at 11:05. All right, hello everyone. So we're back from our break. So we'll go ahead and start sharing the screen again. Let's make sure I can, right, there we go. So we left off with activation energy. And activation energy is the energy barrier between reactants and products. And EA, or activation energy, is the minimum amount of energy required for a molecular collision to result in a reaction. So, go ahead and write down that definition. And make sure that you get your chapter 5 homework done for tonight. So if you're listening asynchronously, the chapter 5 homework is due tonight. So just please make sure that you don't miss that opportunity, for those points. So, homework is an easy way to gather a bunch of points. Activation energy is the energy barrier between reactants and products. As the activation energy increases, the number of molecules possessing enough energy to react decreases. So you can see that right here. As we go to the right, the number of molecules decreases. You can see that right here. We have a high point right here, though. So we transition up, and then eventually we come back down. And what makes catalysts so useful is they lower the activation energy. So you can see in the graph, we end up at the same place. We start at the same place. But what's different? It's the activation energy. So when we decrease the activation energy, we get a faster rate. And that's what they're saying right here. So raising the temperature will result in a faster reaction. You can see that right here. We increase temperature. We have a faster reaction. We can see that, at higher temperature, more molecules will have enough energy to produce the reaction. So we have this many more molecules. I briefly talked about this, towards the beginning of this lecture, to consider sterics. Steric hindrance and the geometry of a compound will affect the rate of the reaction. So if you have something more bulky, it's not going to be, reactions are not going to take place as fast. So molecules collide, they must have the correct orientation. If the reactive conformation of a compound is high in energy, it will spend less time in that conformation, and so the probability of collision resulting in a reaction is low. A catalyst speeds up the rate of the reaction by lowering the activation energy. And it says the catalyst is not being consumed, but over time those catalysts go bad. I'm just letting you know that. So recall that kinetics and thermodynamics are completely different concepts. So here, the kinetics is the rate of reaction. Thermodynamics, will the reaction even take place? We talked about diamond going to graphite. Yes, thermodynamically, this is going to happen, where you have diamond here, you have graphite here, but kinetically, it's not going to happen. The kinetics might be like something like this, so where, we just have such a high barrier that it's not going to be kinetically favorable. It says kinetics versus thermodynamics. Consider this energy diagram, which describes two possible reaction pathways of A and B. The formation of C and D has a lower activation energy. If we just look at the activation energy, this is here versus this one right here. We do see that it's lower. So products C and D form faster than E and F, and C and D are more stable than E and F. So the formation of C and D are kinetically and thermodynamically favorable because one, it has a lower activation energy, and here you can see it's further down. Here, the products C and D are lower in energy, but it has a higher activation energy. So the formation of E and F is kinetically favored. So E and F, this is kinetically favored since it has a lower activation energy. But thermodynamically, C and D are more thermodynamically, that would be the products that are thermodynamically favored. So that's the difference between the thermodynamically favored and kinetically favored. says transition states versus intermediate states. So a transition state is the high energy state that a reaction passes through. You're not really going to see it. You're not really going to observe it. So transition states on this energy diagram, they're at the energy maxima. So they're going to be at the energy maxima. And we can see that here, here, and here. And they give the definitions on the next slide. So transition state is a high energy state. You can see that it is in a higher energy state. They can't be observed, and they are energy maxima. So basically what you have right here, you had a molecule that looked like this, right? And this bromine is coming in to attack. And here's that transition state right there. So there's gonna be a transition where the bromine's coming in, the chlorine's leaving. So you have bond breaking and bond forming. So actually I drew this, sorry about that. So in this case, you had bromine already there. And that chlorine's coming in, and this is bonds being broken, which is shown right here. And we have that chlorine bond being formed. And eventually what you're gonna have is then this. And then you're gonna have that bromine out on its own, and it's gonna go attack something different. And they show it to you down below. So an intermediate is an intermediate species formed in the course of the reaction. They occur at energy minima. We can see that right here, energy minima. And intermediates are observable. They are an actual chemical species that exists for a period of time before reacting further. So at the point that the bromine is gone, you're going to have this carbocation. Well, then what's going to happen is this, eventually form that. So the Hammond postulate, 2 points on an energy diagram that are close in energy should be similar in structure. So that's what they're saying right here. So on this energy diagram, we see we'll call it point A and point B. And we see that they do have similar structure. It's just at point B, the bromine is getting further apart. And if we go down even further, let's just call this point C right here. Maybe that bromine is, here. I'm just trying to exaggerate this. Maybe that chlorine is real close now. So, that's what they're trying to show you right there. So in exothermic reaction, the transition state resembles the reactants. And endothermic reaction, the transition state resembles the products. So here we have exo. Remember, we're going down. Endo, we're going up. And that's what we talked about in the beginning. So polar reactions involve ions as reactants, intermediates, and/or products. Negative charges attracted to positive charges. So electron-rich species are attracted to electron-deficient species. So let's try to make some sense out of that. Negative charges attracted to the positive charges. So here we have this, the carbon atom is electron deficient right here. And that's because this chlorine right here is pulling all that electron density. The carbon atom is nucleophilic, so that lithium is pushing in, or the carbon is taking away the electron density right here. So here the carbon atom is electron deficient, here it's electron rich. We can kind of observe that by looking at the electronegativity chart. Carbon is more electronegative than lithium, so it's going to have more electron density, therefore it's going to be more electron rich. If this is a partial positive, there'd be a partial negative here. Right here would be partial negative, this would be partial positive. So we go into what a nucleophile is. So here, we said that this was a nucleophile from the previous slide. So nucleophile is electron-rich species that can donate a pair of electrons. So nucleophiles are Lewis bases. Remember, a Lewis acid is an electron acceptor. So this is electron acceptor. A Lewis base is electron donor. So the more polarizable nucleophile, the stronger the nucleophile. Here we can see that the electron density would really be concentrated on this ethoxide, so it'd be a really good nucleophile. So if we had something like this, it's a positive, it's going to come and attack right there. Then you'd be left with something like that. So electrophile is electron deficient. We talked about the definition of Lewis acid on the previous slide. Carbocations and partially positive atoms are electrophilic. I gave you that example here, coming into attack there. So here's your nucleophile. I'll just call it nuke. Here's your electrophile. I'll call it elec. And your nucleophile is going to attack at that carbocation right there. And what type of orbital is this? This is a p orbital. It says nucleophiles and electrophile, label some possible examples. So this would be a good electrophilic site. This would be a good nucleophile. You know, right here, you could possibly have electrophilic site. This could be a nucleophile. So that's what they're trying to infer right there. The empty p orbital for a carbocation. Lone pairs are good nucleophiles, and we see that this would have, you know, lone pairs right there. This one would just have one lone pair because you'd have 6 minus 5 equals +1. That's how you get the +1. So curved arrows are used to show how electrons move as bonds are breaking and forming. And we've been showing that to you. I've been demonstrating that to you. So here, you know, we have this nucleophile. You know, it's going to take this proton right here. We have a bond formed and we have a bond broken. So we have a nucleophilic attack. We have a loss of a leaving group. Our leaving group is A in this case. We can have proton transfer, acid base, and we have rearrangements. Here they're showing you a nucleophile, electrophile, the reaction. So nucleophilic attack attacking on an electrophile. A nucleophilic attack may require more than one curved arrow, as we can see right here, because if we just left one arrow, let's just do that, for instance. Here, carbon has 4 bonds already. Now, if we just put this here, now it has 5 bonds, you know, and, you know, generally carbon's not going to have 5 bonds. That's why we're drawing this arrow simultaneously, because we have a bond formed and we have a bond broken. And that's how we get this right here. So it says the alcohol, and this is the alcohol, attacks the carbon with a delta positive charge, because here is delta negative and delta positive. The second arrow could be thought of as a resonance arrow. So, you know, this is coming, this lone pair, this bond, this double bond from the carbon to oxygen is being broken, and the electrons are going to be pulled towards that oxygen. It's electronegative, right? It can take more electrons. The second arrow could be thought of as a resonance arrow. And they're showing you that resonance arrow here. Or if it comes there, but it can also come back down here too, right? To go back here. So we talked about oxygen atoms having lone pairs of electrons to do a nucleophilic attack, but also, you know, if a compound like this, remember we talked about this right here, and this could go here, and this could go here, and this goes here. Well, this is the same concept right here. So pi bonds can also act as a nucleophile. Here we see this pi bond right here. It's attacking this sulfur group. The electrons are going to be then put on the oxygen group, and we can have that bond formed. Just note that only one of the carbon atoms from the pi bond uses the pair of electrons to attack the electrophile. So loss of a leaving group, hydrolytic bond cleavage. Remember, what was a homolytic bond cleavage? A homolytic was just a half barb right here and a half barb right here. I should have drew that better. This would be a homolytic. But hydrolytic, the electrons are going to the bromine. Then we have this carbocation. It's common for more than one curved arrow to be necessary to show the loss of a leaving group. You can also have electron density, move. So we're going to start here. This is where you'd start. It comes here. Second, it'd come here. Third, this would be the first step. Second step, third step, and then fourth step. But it happens simultaneously, but that's how the electrons would start pushing. So then if we did all that, we'd have something like we're going to have proton transfer. Recall that proton transfer requires two curved arrows. So we're showing the proton transfer right here. Deprotonation is the opposite of proton transfer. We're going to take away that proton right here. And it can sometimes be shown with just a single arrow. And that is the single arrow. Here's a double arrow. But it may be necessary, as in this example is showing, multiple arrows may be necessary to show the complete electron flow when a proton is exchanged. So here we have a hydroxide group. It's going to take that hydrogen right there. And once it does that, you're going to get this right here. That double bond will be here, and these electrons will be here now. And once we get this, it can also go revert back and put the electrons right here. That's what this is showing right here. In this case, when we put the electrons right here, now we have this structure right here. Then they go into this topic towards the end of this chapter with rearrangements. So carbocations can be stabilized by neighboring groups through a slight orbital overlap. And the reason why they do this rearrangement is it becomes more stable. So you can have methyl rearrangements and you can have hydride. So a hydride, they call it a hydride shift, where you're going to move a hydrogen from one carbon to another one, or you can have a methyl shift, where you move a methyl group to another carbon. So it's either a hydride or a methyl group that'll be moving. And that's all due to, what is it going to be, make it more stable? And here's the stability chart. So a tertiary carbon is the most stable, and the methyl carbocation is the least stable. So increasing the substitution, what do we mean by increases in the substitution? We're adding more R groups, adding more R groups. Increases the stability. You can see we have one R group, we have two R groups, now we have three R groups. Due to the increasing number of adjacent sigma bonds aligned with the empty p orbitals. And this will be the last slide that we leave off. I don't know why they call it a methide shift. It's a methyl shift. I think they misspelled right here. It's a 1,2 methyl shift. This is a 1,2 hydride shift. So you have that going right there. And if we look back, why is this more favorable? Here we have a primary. This is a primary versus a secondary. So let's see. Actually, there, two. So this would actually be a secondary. Sorry about that. This is a secondary. Everyone see why you have that methyl group right here, and then you have this carbon right here. This is the tertiary then. That tertiary has three R groups. Here we can see we have an R group here, an R group here, and an R group here. So we went from a secondary to tertiary, so that's why we're doing that 1,2 hydride shift. Likewise, the methyl shift is happening because this is a more stable carbocation. So this is the most stable carbocation. That's why we're doing these shifts. And I think that's a good spot to leave. So I'm going to stop sharing. I'm going to pause the recording. So have a great day, everyone. Remember to get your homework done.